Welcome to Basic Electrical Engineering lecture series. This is a series of lecture videos for the first year engineering and electrical diploma students. In these videos, fundamentals of DC and AC circuits, network theorems, fundamentals of transformers, DC and AC machines, and renewable energy sources are the topics covered. Sufficient number of numericals are worked out in each session to make the concepts clear to the viewers. For a basic idea about the topics mentioned, please watch these videos from the very beginning itself. If you find the videos useful, please subscribe for the channel, like the video and press the bell icon for notification. Please try to wear a headphone and watch the video for better sound clarity. Thank you all. And now let's start with today's session. So in today's session, we are covering constructional details of the transformer, its efficiency, regulation, and a few worked out examples. So we know that the main parts of the transformer are core and two windings. Minimum two windings are required and a core is required. So core is providing a tight magnetic coupling between the windings. So core, the most commonly used core materials are silicon steel and CRGO steel. Steel having a few percent of 3 to 5% of silicon content, or cold rolled grain oriented steel. These are the two materials very commonly used for construction of the core. Now the advantages are that these materials are having high permeability and high resistivity. So high permeability means its advantages are it reduces leakage flux. Because if the permeability of the material is more, we can say the permeance of the path is higher. So since the permeance is high, the amount of flux which is leaking out or completing its path through air, it will be less. So in previous session, we have seen leakage flux. So a portion of the flux produced by the primary is completing its path through air, not through the core. This flux is called the leakage flux. It has got negative effects on the performance of the transformer. So if the material used has a high permeability, the magnetic path will be having high permeance and certain amount of leakage flux is reduced. So if leakage flux is reduced, the induced EMF due to leakage flux that will be reduced, or we can say the leakage reactance of the transformer is less. Leakage reactance of the transformer less means the voltage drop due to leakage reactance will be less. So by using a high permeability material, there is an overall improvement in the performance of the transformer. And also high permeability material reduces magnetizing current. So that means to produce a certain amount of flux, say the flux through the core or flux density is a design parameter. That means depending on the kVA rating of the transformer and the voltage ratio, there should be a certain amount of flux density in the core. So we cannot reduce it according to our convenience. So since to produce a certain amount of flux density, if the material is having high permeability, then less current only is required. That means flux is equal to mmf by reluctance. Permeance is the reciprocal of reluctance. So to produce a certain amount of flux or to produce a certain amount of flux density in the core, if permeance is high, then current required will be less. Permeability is a magnetic conductivity. Say if conductance of a conductance in an electric circuit is more, then same EMF can circulate more current, or To circulate a certain amount of current, only less EMF is required because conductance is high. Similarly, if permeance of the magnetic path is high, then less current can produce the same amount of flux or same flux density in the core. So there is a reduction in magnetizing current. So magnetizing current is less means the magnetizing current will be flowing through the winding, so it produces a certain amount of I star R loss. Even though not considerable, a small amount of I star R loss is produced by this magnetizing current. But since a transformer is a device which is always connected to the supply around the clock, so even a slight reduction in losses can contribute to big saving when we consider its life period or a certain amount of periods. So high permeability material, it reduces leakage flux and also reduces the magnitude of magnetizing current. Then the next advantage of this core material is high resistivity. So if the resistivity of the core material is high, then resistance of the lamination will be higher and magnitude of eddy current will be less, so eddy current loss will be less. Say an approximate equation for eddy current loss is K B max square into F square T square watts per meter cubed. B max is the maximum flux density. Told it is a design parameter. Frequency, the transformer is expected to operate at a particular frequency. Say in our country it is 50 hertz. So in certain other countries it is 60 hertz, like that. So to reduce eddy current loss, we can't do anything with the flux density or frequency. So one thing we can do is the thickness of lamination. So in this equation, T is the thickness of lamination. We use a thin lamination to reduce eddy current loss. In addition to that, another factor on which the eddy current loss depends is the resistivity. K is proportional to resistivity, or K includes the factor resistivity. So if resistivity is high, for the same dimension core material or core lamination, resistance will be higher and magnitude of eddy current will be less, eddy current loss will be less. So these are the advantages of using this kind of these core material, that is silicon steel and CRGO steel. This has got high permeability and high resistivity. So high permeability reduces leakage flux and magnetizing current, and high resistivity reduces eddy current loss. So there are two types of core that is this used in transformer construction, or two type of transformers are there: core type and shell type. So these are laminations. The laminations of core type transformer, we can use this L shape and U shape. This is L shape lamination. This is U and I. So this kind of laminations are used for constructing the core. So between two lamination, there will be a certain insulating material, so that two laminations are electrically separate. So shell type transformer, see this is E and I. E-shaped lamination and I-shaped laminations are used for constructing shell type transformer. Now if we make a comparison between these two types, core type and shell type transformer, see, core has got two limbs. Here a table is given which gives a comparison between core type and shell type transformers. Core type transformers has two limbs and two yokes. So core type transformer is like this, what is shown here. These are the two limbs. This is a one yoke, one more yoke. So there are two limbs and two yokes. Whereas the shell type transformer has got three limbs and two yards. Shell type transformer is the front view is like this. So one limb, second limb, third limb, upper ear, lower ear. So there are three limbs and two yards. Then the next point is core is square cruciform. For core type transformer, core is square cruciform or stepped. So that is the cross section of the core. Square cruciform, somewhat like this. Stepped means if more are there, say this is a step construction, square, cruciform, or a certain definite number of steps. So the advantage of stepped construction is that if we draw the outline, it is somewhat circular in shape. So here, if you put the winding is placed over it, it will be like this. That is, free space is more here, whereas in this case, the free space is less. So the advantage of this kind of a construction is that the leakage flux will be less. I already told you the advantages of reducing leakage flux. Leakage flux is less means leakage reactance drop is less. Better voltage regulation can be obtained. That means or the drop due to this reactance can be reduced. Voltage drop can be reduced by reducing leakage flux. So a suitable type of cross section can be used in a transformer while designing it. Square, unique, square, cruciform, or higher number of steps can be used in a transformer core design. So for core type transformer, core is square, cruciform, or stepped, whereas in shell type of transformer, it is rectangular. Then the core type, there is single magnetic circuit, whereas shell type in two magnetic circuits are there. That means in core type, the magnetic circuit is like this. There is only one magnetic circuit. Whereas in shell type, there are two. So in core type, there is only one magnetic circuit, whereas shell type, there are two magnetic circuits. Then the next point is LV winding is next to the core, HV winding surrounds LV winding. That means in core type transformer, normally while drawing it, we draw primary on one limb and secondary on the other limb. But in actual practice, half the primary is on one limb, the remaining half is on the other limb. This kind of a construction is used again to make the flux distribution more uniform to reduce leakage flux. We can use this kind of an arrangement. That is, low voltage winding is half on one link or remaining half on the other link. Likewise, HV winding is over this. HV winding surrounds LV winding. Half HV winding is on one link, remaining half of the HV winding is on the other link. So LV winding is next to the core. That is due to because of voltage, because the HV winding is at a higher potential, so it should be kept little away from the core. That is why LV winding surrounds the core and HV winding surrounds the LV winding. And moreover, HV and LV both half on one limb, half on the other limb. That is to make a flux distribution more uniform. So this is the type of construction used in core type of transformer, whereas in shell type of transformer, both the windings are on the central limb. Half HV here, half LV here, half LV on the other end, HV in the middle, like that we can put it, or different types of arrangements are there for that. So both the windings are on the central limb. The outer limbs are used for just uh, circulation of the, to complete the magnetic path. Then in core type transformer, less iron is used for the core. That means it has got only two limbs and two yokes, whereas shell type transformer, three limbs and two yokes. The size is also a little bigger. So core type transformer core, only less iron is used, whereas in shell type, more material is used for the core. Next comparison is natural cooling is more for core type transformer. Natural cooling is less. Here it looks, for shell type transformer, it looks the core surrounds the winding. Core is totally enclosed by the winding. Here, in core type of transformer, the winding surrounds the or encloses the core. It looks, the appearance is like that. So here in shell type of transformer, free space is less in between. So natural cooling is bit less. Then easy to core type of transformer. Next advantage is that it is easy to dismantle and repair, whereas shell type it is more difficult because of the same constructional, because of the specific type of construction. Then core type transformer is used for HV and high power application in most of the high power circuit. All distribution transformers and high rating power transformer all are core type only. Shell type is used only for in low voltage circuit, low power circuits, and electronic circuits. And because of this reason, if it is, the natural cooling is less also, there is no problem at all because it is used for very low rating power circuits. Next is windings. Windings are made of copper. So windings are designed for low voltage winding. It is comparatively thicker because the current capacity will be more, and high voltage winding it is thinner, and number of turns will be more because the uh, voltage applied is more. So the winding distribution is, as I told you, in core type transformer. This is LV winding, half of the LV winding, remaining half of the LV winding. Then HV winding, in between little insulation is there. After that, HV winding. This is what I'm drawing here is the cross section. So this is LV, this is HV, all half of it. The remaining half of the LV winding is here. HV winding surrounds that. This is HV, this is HV. So LV winding is next to the core and HV winding surrounds the LV winding. Half of the LV is put on one limb, remaining half of the LV is put on the other limb. Similarly, high voltage winding also half on one limb, the remaining half on the other limb. Shell type transformer, the outer limbs are used only for completing the magnetic path. So LV half here, and HV outside that, in between. HV, LV is also LV. So other type of constructions are also used for shell type of transformers. That means a bit different type of designs are used for shell type of transformers. Then rating of transformer. So you might have seen the rating of a transformer is normally expressed in kVA or MVA. So here we have seen there are two type of losses in transformer. It's a static device, only two type of losses are there. Mechanical losses are not present in a transformer. So the core loss and copper loss. So copper loss depends on current. We have seen an equation for copper loss. This is I1 square R1 plus I2 square R2. So copper loss depends on current. And also core loss depends on voltage. Normally transformers are operated at the rated voltage, so core loss is constant. So as far as a transformer is concerned, we consider core losses constant and copper losses variable. So core loss is a constant because it depends on voltage and transformers are operated at the rated voltage only. Copper loss, it depends on the fraction of the current. So always a transformer need not be operated at the rated current. The load can be half or 1/4 or 3/4 or something like that. So accordingly, copper loss also varies. Say copper loss is roughly this I square R loss only happening in the winding. If current is reduced to half, then the copper loss will be I square I by 2 square into R. That will be the equation for copper loss, I by 2. Here current is full load current is used or rated current, if rated current is high, the copper loss will be I square R. If current is reduced to half, then I by 2 square into R. That is I square R divided by 4. That means copper loss is reduced to 1/4. So if current is reduced to half, copper loss is reduced to 1/4. So copper loss is considered as a variable loss. So since the losses are dependent only on voltage and current and not on power factor. So the angle between voltage and current is not coming to the picture at all as far as the operation of a transformer is concerned. So the rating of the transformer is expressed in volt ampere or kilovolt ampere or megavolt ampere and not on kilowatt. Next is the EMF equation of the transformer. So the equation for circulating flux through the core. This flux is produced by the current. Say primary current is I. This produces a flux phi in the core. So this is the RMS value, instantaneous value. If I write, if I take I is equal to Im into, it's a sinusoidally varying quantity. So applied voltage is sinusoidal. The current through the winding also sinusoidal. So the flux through the core is also sinusoidal. So let's take the instantaneous value of flux through the core is pi m sin omega t. So voltage, applied voltage, current through the winding, and flux through the core, all are sinusoidally varying. There will be phase difference among these quantities. Let's not bother about that. Let's consider that all these quantities are sinusoidally varying. So phi is equal to phi m sin omega t. So induced magnitude of induced EMF. So we know that induced EMF is minus N into d phi by dt. So induced EMF per turn is minus d phi by dt. So let's take only the magnitude of that. So it is d phi by dt. So or d by dt of phi m sin omega t. What is d by dt of phi m sin omega t? Phi m into omega into cos omega t. So what is omega? Omega is 2 pi f. So phi m into 2 pi f into cos omega t. Or 2 pi phi m of cos omega t. So this is the instantaneous value of induced EMF per turn. Phi m into omega into cos omega t, or 2 pi into phi m into f into cos omega t. So from here, from this equation, it is clear that this is the maximum value of induced EMF. This is the induced EMF per turn. Instantaneous. This is the instantaneous value only. This is so EM is equal to maximum value of EMF per turn is equal to 2 pi into phi MF. So what is the RMS value? Maximum value divided by root 2. 2 pi into phi MF divided by root 2. We get to root 2 pi phi MF. Root 2 pi is 4.44. 4.44 phi MF. So this is equal to 4.44 phi MF. So this is the RMS value of EMF per turn. So what is the RMS value of primary induced EMF E1 is equal to EMF per turn into number of turns in the primary winding. Let there be N1 turns in the primary winding, then E1 is equal to 4.44 pi M of N1, and E2 is equal to, there are N2 turns in the secondary winding, so secondary EMF is 4.44 pi M of N2 volts. So these are the EMF induced in the primary winding and secondary winding. So this is the instantaneous value of flux by using the equation. Magnitude is equal to d phi by dt. We are not considering the minus sign. We need only the magnitude. So while differentiating, we'll get this equation 2 pi f phi m into cos omega t. So this is the instantaneous value of induced EMF. So this should be the maximum value EM. So it is Em cos omega t. So Em is 2 pi phi m of. So this is the maximum value. So RMS value is that divided by maximum value by root 2. So you will get 4.44 phi m of, which is the RMS value of EMF per turn. Multiplying it with number of turns in the primary and secondary windings, you will get the primary induced EMF as well as secondary induced EMF. So from this equation, E1 by E2 is equal to N1 by N2. Straight away, if you divide, you will get this equation. So this ratio, primary induced EMF ratio, the ratio of primary to secondary induced EMF is equal to N1 by N2, which are the number of turns. Turns ratio is equal to voltage ratio. So next is the efficiency of a transformer at rated output and at the different fractions of the load. So the general equation for efficiency is output by input. So input can be expressed as output plus losses. So what is the output of the transformer in terms of its kVA rating? kVA is kilovolt ampere. So output of the transformer is kVA is kilovolt ampere. So kVA into 1000 will give volt ampere into power factor, operating power factor. That is the output in watts. So that is nothing but VI cos phi. VA is volt, kVA is kilovolt ampere. kVA into 1000 is volt ampere. That is voltage into current, V into I, into power factor. That is the output in watts. So kVA into 1000 into cos phi is the output in watts. So output divided by output plus core losses plus copper losses. So this is the equation for efficiency. Say let WCU be the full load copper losses and WC is the core losses. Say core, let copper loss at rated load is I square R. Then at half load it is I by 2 square into R or 0.25 I square R. So generally we can write if it is 3/4 load, at rated load it is I square R. At 3/4 load it is 0.75 square into I square R. So like that, generalizing, if the transformer is operating at fraction x of the rated load, a half load means x is equal to half. Quarter load means x is equal to 1 by 4. Or any fraction of the load. X is equal to 0.1 means 10% of the rated load. So the copper loss at fraction x of the load is x square into WCU. We can generalize it because WCU is the copper loss at rated load. By multiplying it with x square, we can find out the copper loss at a fraction x of the load. So the efficiency equation can be written like this. X kVA 1000 into cos square, x is the fraction of the load. If the transformer is operated at half load, x is equal to 0.5. If the transformer is operated at 20% of the load, x is equal to 0.2, like that. So x kVA cos phi into 1000 divided by, which is the output, this is the output, plus core loss plus copper loss. So because at the fraction x, copper loss is x square into copper loss at the rated load. So this is the final equation for efficiency of a transformer. That is x kVA into 1000 into cos phi divided by x kVA into 1000 into cos phi plus core loss plus x square into copper. This is WC is copper loss at rated load. Or x is equal to 1. This is core loss is constant. For all fractions of the load, core loss is constant. So this is the efficiency equation. Next, what is the regulation of a transformer? So regulation is, equation is this E2 minus V2 divided by E2. E2 is the secondary voltage at no load. Primary is the source here. This is V1. V1 and E1 normally for in our computation we will take it as the same. We won't consider the. Now this is E2, V2. Now V2 is equal to E2 at no load. Terminal voltage is equal to, or if we neglect the voltage drops, then V1 is equal to E1, E2 is equal to V2. But regulation considers the voltage drop. So at no load, when no load means when there is no current flowing in the secondary circuit, then E2, V2 both are same. So this is the secondary terminal voltage at no load. Then load is connected here. This is load. When load is connected here, there will be a voltage drop in the secondary winding. That is due to the resistance as well as the leakage reactance. So V2 will be less than when current is flowing through the secondary winding. V2 will be less than E2. So that difference, and this is only the magnitude difference, not phases. So E2 minus V2 divided by no load secondary voltage minus full load secondary voltage divided by no load secondary voltage. This ratio is called regulation of the transformer. So the less the voltage drop, it is better. So voltage drop is happening due to the resistance as well as leakage reactance of the winding. So let's work out some examples. The first one is a single phase transformer has primary and secondary voltages of 4000 volts and 400 volts. Supply frequency is 50 Hertz and peak value of flux in the core is 0.05 Weber. Find the primary and secondary number of turns. So the equation for induced EMF is E1 is equal to 4.44 pi m of N1 and E2 is equal to 4.44 pi m of N2. So primary and secondary voltages are given 4000 volts and 400 volts. Here the primary voltage drop or such details are not given. So we have to take V1 is equal to E1, V2 is equal to E2. So voltage, applied voltage or what is primary voltage is 4000 volts, secondary is 400 volt. That means E1 is 4000, E2 is 400. So maximum value of flux in the core is 0.05 Weber. Then frequency is 50 Hertz. So F is equal to 50 Hertz. Maximum value of flux in the core phi m is equal to 0.05 Weber. So E1 that is 4000 is equal to 4.44 phi m, that is 0.05 F, that is 50 into N1. So N1 is 360. Secondary voltage E2 is equal to 4.44 pi m, that is 0.05 into 50 into N2. So N2 is 36. So primary turns 360, secondary turns 36. Next. A single phase transformer rated at 5 kVA, kVA is equal to 5. Frequency is equal to 50 Hertz. N1 is equal to 360. N2 is equal to 240. The EMF per turn, secondary EMF per turn in the secondary. Secondary EMF per turn is 2.5 volts. The induced EMF per turn in the secondary, in primary and secondary EMF per turn is the same. So respective of primary and secondary, EMF per turn is 2.5 volts. So we have to find out the primary and secondary voltages and rated currents. So the voltage can be found. The primary voltage is equal to EMF per turn into number of turns in the primary winding. EMF per turn is 2.5. Number of turns in the primary winding is 360. So 900 volts. Then secondary voltage E2 is equal to EMF per turn into number of turns in the secondary winding. 2.5 into 240, that is 600 volts. Now next we have to find out the rated current. Rated current is equal to kVA rating is the same on either side of the transformer. V1 I1 is kVA, V2 I2 is also kVA. So in this case V1 is equal to E1. So E1 I1 is equal to E2 I2 is equal to kVA into 1000. kVA is kilovolt ampere. Multiplying with 1000 will get volt ampere. So E1 I1 is equal to E2 I2 is equal to kVA into 1000. So from this I1 and I2 can be found out. So E1 I1 is equal to E1 I1 is equal to 5 kVA, that means 5000 volt ampere. So I1 is equal to 5000 divided by 900. That is 5.55 ampere. Then E2 I2 is also is equal to 5000. That is I2 is equal to 5000 divided by E2. E2 is 600. So 5000 by 600 is 8.33 ampere. So primary current is 5.55. Secondary current is 8.33. Then A 125 kVA transformer. So kVA is equal to 125. Primary voltage, that is E1, is equal to 2000 volts and frequency is equal to 60 hertz. If the number of turns of the primary N1 and secondary are N1 is equal to 182 and N2 is equal to 40. Find the maximum value of flux in the core and rated currents. Find the secondary voltage, that is E2, maximum value of flux in the core, that's 5M, and the rated currents, primary current and secondary currents. So primary voltage is given, number of turns are also given. So we can use this equation, E1 by E2 is equal to N1 by N2. E1 is given, that is 2000 volt. E2 we have to find out. N1 is 182, N2 40, from which E2 is 440 volts. Then to find out phi m, we can use one of these equations. That is, E2 is equal to 4.44 phi m of N2, or E1 is equal to 4.44 phi m of N1. Choose one of these equations and find phi m. Says, using the second equation, that is E2 is equal to 4.44 phi m of N2. So E2 is 440, we found out. 4.44 into phi m into F is 60 hertz and N2 is 40. So from which phi m is 0.0413. Now primary current is, so kVA into 1000 divided by E1. E1 I1 is equal to E2 I2 is equal to kVA into 1000 or volt ampere. So kVA into 1000 divided by E1 is equal to 125,000 divided by E1 is 2000. So we will get 62.5 ampere. Secondary current is kVA into 1000 divided by E2, 284.09 ampere. Next. In a 10 kVA transformer, the core loss is 140 watts. WC is equal to 140 watts. Full load copper loss, that is WCU, is equal to 160 watts. Find the efficiency of the transformer in these three cases. First one is full load UPF, half load 0.8 power factor, 3/4 load 0.9 power factor. So full load UPF means full load X is equal to 1 and UPF means unity power factor, cos phi is equal to 1. Then half load 0.8 power factor. Half load X is equal to 0.5 and power factor is 0.8. Third case, 3/4 load 0.9 power factor. That is X is equal to 0.75. Cos phi is equal to 0.9. So we can substitute in the equation x kVA into 1000 into cos phi divided by x kVA 1000 into cos phi plus WC plus x square WC. So in first case x is equal to 1, kVA 10 into 1000 into cos phi 1. X kVA into 1000 into cos phi plus WC is 140 plus x square, 1 square into 160. M square is 1 into 160. You get 97.08%. Second case, x is equal to 0.5, kVA 10,000, cos phi is 0.8, divided by x 0.5, kVA 10 into 1000 into cos phi 0.8, plus WC 140, plus x square. X is equal to 0.5, so x square is 0.25, so this is 0.5 square. X square into WC 160, get 95.69%. Third case, x is equal to 0.75, kVA 10 into 1000 cos phi 0.9, x kVA 1000 cos phi plus WC plus x square 0.75 square. This is 0.75 square into 160. That is 96.7%. A 5 kVA transformer having a core loss of 100 watts. WC is equal to 100. Has efficiency 95%, efficiency 0.95. At full load UPF, x is equal to 1, cos phi is equal to 1. Find the efficiency at half load 0.8 power factor loss. So we have to find out the efficiency at half load. X is equal to 0.5 and cos phi is equal to 0.8. So substituting in the equation, efficiency is 0.95. 0.95 is equal to x. X is 1. X kV is 5 into 1000 into cos phi is 1 divided by x kVA 1000 cos phi plus core loss is 100 WC plus WCU. So in the first case, x is equal to 1. So the term here is the full load copper loss. So WCU, there is no x here. X 1 square is 1 only. So from this equation, we can simplify it. That is 0.95 is equal to 5000 divided by 5150 plus WCU. So full load copper loss is 163.15 watt. So now we can find out the efficiency at half load 0.8 power factor. That is equal to x is equal to 0.5 and cos phi is equal to 0.8. So x kVA 1000 into cos phi. X is 0.5, cos phi is 0.8 divided by x kVA 1000 cos phi plus WC plus x square. X is 0.5, so x square is 0.25. So 0.25 into 163.15. So the answer is 93.42%. Then a 25 kVA transformer has kV is 25. Core loss of 350 watts and full load copper loss 400 watts. Has an efficiency of 96.31%, 0.9631. At cos phi is equal to 0.8. Find the fraction x of the full load at which it is operating. So efficiency is 0.96. We can substitute in the general equation. So efficiency is 0.9631 is equal to x is not given. X kV is 25,000. Cos phi is given 0.8 divided by x kVA 1000 0.8 plus core loss is 350 plus x square into full load copper loss. Full load copper loss is 400. So solving this, we can find out the value of x. So 20,000 x divided by 20,000 x plus 350 plus x square into 400 is equal to 0.9631. Simplify to this form. So we get a quadratic equation. Solving, we get 0.751 and 1.163. That is at quarter load, 75% of full load and 116.38% of full load. The value of for the efficiency is 0.9631. Next, a 10 kVA transformer has an efficiency of 98% at full load, 0.8 power factor, and 97.5% at half load UPF. Find the efficiency at 3/4 load, 0.9 power factor. So kV is equal to 10 Then efficiency is 0.98. At full load 0.8 power factor. X is equal to 1. Cos phi is 0.8. This is one case. The next case 0.975. Efficiency is 0.975 at half load UPS. So efficiency is equal to 0.975. X is equal to 0.5. Cos phi is equal to 1. So solving these two equations, we have to find the core loss and full load copper loss. Here also KVA time. This is one case. This is the other one. So efficiency is 0.98. So X is 1, KVA 10 into 1000 into cos 5.8 divided by X KVA into 1000 into cos 5.8 plus WC plus X square. X square is 1 into WC. That is the first equation. Second case, the efficiency is 0.975. So 0.975 is equal to X 0.5 and cos phi 1. X KVA 10 into 1000 into cos phi 1 divided by X KVA 1000 cos phi plus WC plus X square is 0.25 into WC. So first equation can be simplified to WC plus WC is 163.26. Second equation WC plus 0.25 WC 128.28. Solving this, we can get WC is 116.6 and WCU is 46.66. Now with this information, we can find the efficiency at the 3/4 load 0.9 power factor. Substitute in this. So 3/4 load means X is equal to 0.75 and power factor cos phi is equal to 0.9. So efficiency is equal to X, that is 0.75, KVA 10 into 1000 cos phi 0.9 divided by X KVA 1000 cos phi plus WC. WC is 116.6 plus X square. 0.75 square is 0.5625. 0.75 square into full load copper loss is 46.66. So efficiency at the 3/4 load 0.9 power factor is 97.93%. So two sets of informations were given. With that, we found out the core loss and full load copper loss. Once we obtained core loss and full load copper loss, we found out the efficiency at a given fraction of load and given power factor. So that's all for the session today. Thank you very much for attending this session. If you like this session, please subscribe for this channel and press the bell icon for notifications. Thank you.